where a number of students from across India are being mentored by a number of other students and some scientists. I think the number, as previously told, is around 45. And we are having this lecture series weekly for the students who are part of this Teach for Science program. And I think other attendees are also welcome. And it has been a very fruitful lecture series, I would say. And this lecture today by Dr. Pooja is going to be the last one to conclude our Teach for Science program. And the part which is to be followed is submitting proposals and submitting the research schemes and stuff. So without any further delays, I would like to start with the lecture, and I would like to formally introduce Dr. Pooja before that. Dr. Pooja is a principal scientist at CSIR CSIO, and her major research area is material science and sensor applications. She did her PhD in engineering from Academy of Scientific and Innovative Research, New Delhi, and has a MTech degree from Indian Institute of Technology, Roorkee. Her doctoral thesis work was awarded J.C. Jain Memorial Best Thesis Award by Material Science Research Society of India. Her work is mostly on applied material science with a focus on developing materials and methods for energy and environmental application. And the major research interest includes materials and device designing for hydrogen production, water-air pollutant degradation, and water pollutant monitoring. She has a very versatile, I would say, track record, and has published around 72 research publications, edited 5 books as lead editor, a number of book chapters. She has filed 3 patents, 1 copyright and 1 trademark, and has been developing technologies which can be transferred to industries. And there's a long list of various awards and fellowships which she has been awarded, including Haryana Yuva Vigyan Ratna Award, INAE Young Engineer Award, Sir Women Scientist, Women Excellence Award, Young Associateship of Indian Academy of Sciences, Young Scientist Award from Indian Science Congress Association, Young Scientist Award from International Society of Energy, Environment and Sustainability, Canadian Commonwealth Fellowship, and the list is too long. And she has been serving as a member of various academies, including INAE, IASC, and NASI, and she's also core committee member of INYAS. She has mentored number of students, and she's also guiding 4 PhD students in, besides her research activities and numerous awards. She is also engaged in various science outreach activities, and INYAS program is one of them. And I thank Dr. Pooja for being with us today for this. I think this could have not, there could have been no better concluding talk than having you as one of the speakers for the Teach for Scientists program. So Dr. Pooja, I welcome you, and the stage is all to you now.
Thank you, Bindya. And I think it's really fortunate for us as on behalf of INYAS, I would like to say that we could collaborate with the INYAS, which is I think a very well-doing NGO working in the Punjab area, and we could reach to the students in particularly in this particular region. So that's also one mandate of the INYAS, reaching to the people in the regional level through local chapters and all these things. So Yatin approached me for this, and I'm happy we could make it. We started this collaboration, and I look forward to further future collaborations in similar lines. So I was, since I am the last speaker to conclude this series, so I thought I would be sharing more kind of the work which we are doing in my group, especially for with focus towards sensor materials. Though we are working significantly in the recent last couple of years on to catalysis also, but I'm not going to cover that. So let me start by first sharing my screen. So I'll be happy to get the question, and would be happy to have this interaction more interactive. And I also look forward to good students who are willing to join my group as an intern, or maybe to one or other form they want to work in the domain which I am working upon. So I'll be happy to interact with those students as well. So for today's talk, I decided to speak upon materials for optical detection of water pollutants. So my group, like I said, we have been working, like I am basically a material scientist by training, more or less had experimental experience onto the material synthesis and their application. So my group started working on exploring these materials for the water pollutant detection. And being from an instrumentation organization that my institute, CSIO, it's an instrumentation organization under the umbrella of CSIR. So we look towards the translation of the materials development into FTKs. We call them as a field test kits. So this is the area which I started working upon. Slowly from 2015 onwards, my group is more or less focused towards developing catalytic materials that include catalyst design for hydrogen generation and catalyst design for indoor air pollutant degradation. So all these domains, they cover three main SDG goals of UN. That includes SDG 6, clean water and sanitation, SDG 7, affordable and clean energy, and SDG 13, that is climate action. So how do we we work in these domains? So being from material science background, what I work upon is engineering of the materials in terms of their shape, in terms of their size, so as to tune their optical, structural, and electronic properties, as well as impart some certain surface functionality, which is very much important, especially for the sensor design. While for the catalysis, the design of an efficient heterostructure is a critical part, because that allows you to have the efficient charge separation as well as the transport of charge carrier, which is required in the catalysis application. So I've been working upon carbon nanostructure, oxide nanostructures, and lately my major focus is on 2D materials that include TMDs, MXenes, TMOs. So these are the kind of material I'm exploring. And the plasmonic nanostructure I have more or less utilized in my sensor development platform, and also the catalysis application as a photosensitizer for enhanced visible light absorption. So I'm going to cover more or less about the sensor part today, but I can take, if anybody has any query, any question related to catalysis, I'll be happy to take that as well. So why we focus towards developing the material for the water pollutant detection, or FTKs? The motivation is, in our country, the water has been a major problem in terms of the quality and the quantity. The quality, in a sense, because being a developing country, so there is a lot of, wastewater which is generated, which is like even after going through the several treatment processes, it's not fully treated and it discharges into water bodies. And in many industries, the water without treatment is discharged into water bodies and soil and the natural habitat, which leads to the contamination of the water resources. In terms of the quantity also, at some places there is a overexploitation of the water, so that the water table has also gone down. So water is really an important factor which is to be looked upon for our country, which is a developing country and seeing a lot of urbanization, a lot of industrialization. And if we see the facts and figure, around 2.95% of our GDPs goes into the management of waterborne diseases, mainly the water contaminated with the inorganic constituent, inorganic pollutant, as well as the biological pollutants. And if we see in terms of the market for the water in technologies, around 32.44% share is of the water sensor market. So that includes all kind of instrumentation, including the laboratory setups we use, such as hand chromatograph or ICP-MS or atomic absorption spectrophotometer. So that covers such kind of setups. They are used for the water testing, water quality monitoring. So this is one aspect of ensuring the quality of the water before consuming it, or also monitor the fate of the pollutant in a particular area. The other alternate is the field test kit, which are more user-friendly. And so we can engage the community by providing them FTK solution, which are, affordable, easy to use, and if are IoT enabled. So we looked into this particular aspect and we found what is the current status. And we see that there are most of the kits which are there into the market, they are mostly imported. And only there are few indigenous players who worked on the design of some of the reagent kit for the heavy metals and biological pollutants. So with this gap, we decided with our expertise on the material science to design some new materials and also work on their chemistry so that we can develop some field test kit based on those materials. And not only developing those materials, characterizing them, studying them for the water pollutant, but also take those materials to the next level, that is to the so that they can be used into the field environment. So we have worked upon certain set of material for various kind of heavy metals and metalloids, but I am going to give an example for one or two to give an idea how we can take our fundamental understanding of the materials into the field ready solutions. So for any sensor platform which we are designing for any kind of application, be it a diagnostic, healthcare, food, or water, first criteria is what kind of transduction technique we are adopting, because based on that technique, we can see the possibility of translation of that technique into the miniaturized devices. So one can work upon any of these techniques, which could be based upon the optical signal change or electrical or the electronic or the Raman based molecular vibrational change. So any kind of change which one can easily monitor can be converted, can be translated further. So the appropriate selection of technique is an important factor for designing any kind of sensor material. Another important factor is from material science point of view, what kind of the sensor platform you are going to adopt. Like if you are using a fluorescence-based technique as a transduction technique, what could be the potential material? They could be like starting from your organic dyes, from your semiconductor quantum dots or carbon dots or metal nanoclusters. So there are a lot of materials which are available for each kind of technique. So appropriate selection of materials is also an important criteria for designing any sensor. And what are the factors which affect the selection of materials? They could be in terms of the safety of the material which you are developing, because finally you are going to use them for the environmental application. So how you can dispose them? Are there any health hazard associated with them? How you can synthesize them? Can you scale those materials? What are the precursor or the raw material behind synthesis of this material? And what is the overall cost of the basically the cost benefit ratio of the process which you are developing to synthesize those material at large scale? So these are some of the important factors which are required to be understood for selecting any material for the which you want to take to the next level, not just to the lab environment. So one of the material which we develop, and we developed this first of its kind platform for the selenium detection in water. Why selenium? Being in this Chandigarh area nearby to Punjab, we get to know with discussion with the Punjab Water Supply Sanitation Board that selenium is coming up as an emerging pollutant in the Punjab area, and there are many districts, many places in Punjab which is reported to have the high level of the selenium. And right now there were no field kits which can be used for the detection of the selenium in water, and so it can be used into the field application. So we adopted this carbon-based platform, which is carbon quantum dots. I think it's a very well-known material in the carbon family. This is the smallest member of the carbon family. We synthesize this material from synthetic route also, and also from the green route. And we optimize the process in terms of their synthesis time, in terms of their synthesis temperature, and we could obtain very highly fluorescent blue quantum dots. These are synthesized from the carbon precursor. So you can see we have done the optimization in terms of optimizing their synthesis time and synthesis temperature, and that has been monitored by monitoring the change in the absorbance as well as change in the luminescence. And also the size is an important criteria for the sensor platform which we are designing, say on the basis of fluorescence. So if there is a uniformity in the size, we generally get an excitation independent emission behavior, which we could see here. But if there is a variation in the size obtained, you will have an excitation independent emission behavior. So then it becomes very difficult to use such cluster of nanomaterial for designing the sensor. So having a uniform size, having reproducibility in the synthesis process is also an important factor for the utilization of material later. So we did all the basic characterization which are required for the materials. So we did the HR time analysis to find out what is the size of these nano quantum dots which we synthesized, and it was in the range of 4 to 5 nanometer. And then we also confirmed, we did, since the carbon quantum dots, they generally have the carboxyl functionality present on their surface, and the carboxyl functionality, they are not selective. They can bind to any kind of the element. So to introduce the selectivity onto this platform, we did synthesize one ligand, which was based on a shift base. So we worked on a basic shift-based chemistry and designed a shift-based ligand from 2 pyridine carboxyldehyde and 1 amine. And this ligand, first we characterize in terms of their FTIR characteristics, their NMR and the MS, that confirmed us that we have synthesized this particular ligand. And after the synthesis, what we did, we functionalized this ligand onto the surface of carbon dots. So you can see these are the FTIR characteristics of carbon dots, and these are of the ligand, where we have the peaks corresponding to the carboxyl group and also the shift base. And when we did the functionalization, we got the additional peak, which is at around 1690, which correspond to amide board formation. So that confirmed that the ligand which we synthesized has been successfully functionalized onto the surface of the carbon quantum dots. So now the surface chemistry of the carbon quantum dots has been changed. So instead of carboxyl group, it has more richness in terms of the nitrogen group. And the nitrogen is known to bind very well with the selenium. Nitrogen selenium chemistry is very well reported in terms of the high bond dissociation energy. So we utilize these functionalized sensor platform, and we did initial characterization also of this functional platform to see how are its absorption, how is its emission characteristics, how its absorption characteristics. And also we did the XPS analysis, which enabled us, which further confirmed us that the additional peak corresponding to the amide board formation in the nitrogen oxygen 1s, carbon 1s, and the nitrogen 1s led us to the confirm that we have the functionalization of the carbon dot with the ligand. So this is how the chemistry looks like. This is, you can see, this is how we synthesize the shift base, and this is how the carbon dots were there and how we made it react to the ligand which we synthesized. And this is how the final structure is. So you can see the structure is more or less rich in the nitrogen elements, so which enabled the capturing of the selenium. This was what our hypothesis is, that it will enable the selective detection of the selenium. So when we tested this functional platforms for the selenium, we did initial screening with the lower concentration and the higher concentration. And we could see that when we started adding selenium to this sensor, we could see there is a decrease in the fluorescence intensity. Even at very high concentration, the overall the platform is kind of totally quenched. So basically, the binding of the selenium, it decreases its fluorescence intensity, and this trend has been very dynamic. We have seen a dynamic decrease in the intensity with increase in the concentration of the selenium. So that gave us very positive aspect that the sensor is responding to the selenium. So we did all other optimization which are required for the field application to explore this material for the different pH environment, different dynamic strength environment, presence of different interfering ion. So we did all those exploration, and these are the studies corresponding to what effect of the pH onto the performance of the sensor platform. And then also, what is the selectivity of the sensor for different kind of anions which could be present into the environment, or the cations, and also the competitive studies. In the competitive study, what we did, we took selenium along with the presence of other elements. So we did two kind of study. One is the comparative and another is a competitive study. So from here, we again got very good satisfactory results, which were comparative. So that shows that the sensor is able to differentiate between the selenium and other element, and it could respond to the selenium even in the presence of other elements or a mixture of elements present into the water sample. So we also started taking the material further, and we started testing this sample with the real water sample, which we collected from the nearby area. And now even this work is still continuing. This is not a completed work. We are now testing these probe which we have designed into the field environment, where we are collecting the water samples pre-monsoon, post-monsoon. Basically 3 times in a season, we are collecting the sample and we are testing the performance of the sensor into the field environment. So this is the example how we converted a simple carbon-based fluorescent probe into a selective probe for the selenium detection in water. Likewise, we worked on the chemistry for iron detection in water, where we use unfunctionalized carbon dots. We utilize the normal carboxyl functionality onto the carbon dot surface for the selective detection of the iron. And likewise, we design another carbon-based probe, which is again for the detection of the chromium, including the total chromium as well as its different oxidation state. So not only developing the material, what we have done, we also designed a portable device where I worked with the people from the other background in my institute. And this device is kind of a very handy device. This device reads the response of the fluorescent probe. So it is a customized device which has a identified excitation for source and identified detector along with the combination of the optical element for detection of a low level detection even up to the ppb level. So having this device, because if you are going to take a fluorescence based platform into the field, you definitely need a reader. So this device was developed in a purpose so that we can take this device into the field and we can study the response of the platform which we have developed. A step further, we also worked on the colorimetric sensor platform, realizing that colorimetric sensor platform are more user-friendly, like because the colorimetric FTKs are very well accepted in test lab, into even normal users, the color-based change is more accepted. So we tried working on the developing the color-based sensor platform. Again, here the platform was the carbon-based nanostructure. So we worked on the cresol red dye, and we pyrolyzed this material under optimal condition. And the best part with this kind of platform is that this carbon platform showed a very selective change towards the arsenic. And that change not only observed by a color change, which you can see from here, but also the appearance of new peaks when we did the optical study with this sensor probe, and we could see there's appearance of a new peak corresponding to arsenic, which was not there for the other element. So this was a very direct approach for the detection of the arsenic, which is not otherwise there for the kind of kits which are available into the market as of now. Likewise, for the selenium also, we also explored the color-based approach for the detection of the selenium, like for the primary screening, where we want to know the range, whether the selenium is present or not. So we worked upon a modified iodometry approach, and we modified the process. We improved the sensitivity of the process. So we could see the presence or absence of the selenium, and this is also very well validated with the spectroscopic studies. So these are some other sensor platform, which we have developed based on the color for the detection of the mercury and the chromium. I'm not going more into detail of them. Now, what additional part we have done in all these color-based sensor platform, the color-based detection is very subjective detection. The interpretation of the color changes person to person. Pink may be something, the grade may be different for me. It may be something else for other. So differentiation of color is a very subjective issue. So sometimes it may lead to an error. So what I did, I collaborated with the people in my institute here who works on the area of computational. So we developed a portable device that device reads the response of the color, it analyzes it, and then it quantified, and then it gives you the result. So we developed this device around the commercial test kit first, which is we started this work with the lead, and now we have extended this device even for the residual chlorine. So you can see this was the very first version of this particular device, and this is the second version. And this is the latest version of the device which we have developed. It is more or less like a USB kind of stick. and you can use it along with your mobile phone. And we also develop a mobile app. So your analysis is done within the device itself, and then the results are analyzed and presented to you. And maybe you can send this result to wherever you want to send, along with the time of analysis, along with the location where you have done the testing. So overall aim of developing such kind of solution around the colorimetric kit is to engage the people into the testing. Because what is the purpose behind all this device integration is to come up with the very user-friendly solution which can be deployed in our household. Like heavy metals may not be of very much use into the household environment, but it is more or less of industrial interest, as well as of interest to the water testing lab. But like residual chlorine is definitely a parameter of interest to all of us, because whatever water we get in our houses is after the chlorination. So many times water get under chlorinated or the over chlorinated, we don't know, and under and over both leads to several health problems. So how to ensure that the water which we are getting is safely treated or not? So that is the reason we have developed this USB kind of stick, and we are hopeful soon we will be bringing it into the market. We are in negotiation with some of the companies. So this is an overview overall what kind of the materials we have worked upon, what kind of the devices we have developed around these materials, so that we can use those materials into the field test field environment. So this is a glimpse of the products which our group has developed. We also have developed some kind of product based on the catalysis. So I am not going more into that particular aspect. So this is vis-a-vis a benchmarking of the test kit which we have developed for the arsenic and selenium to show in terms of the novelty over the commercial products which are available there. Another aspect which I wanted to cover in my talk today is the sensor platform, optical sensor platform for the detection of the organic pollutants. So the detection of the organic pollutants, if we talk about the techniques which can be field usable, which can be field ready, search, or you can say Raman spectroscopy is one such technique, because nowadays thanks to the Professor C. Raman with this effect, now I think this technique has got a lot of application in all the diagnostic, in the pharma sector, in the food sector, and now we even have the miniaturized Raman, handy Raman, which are available. So but the major problem with the Raman remains is the weak signal in certain set of analytes. So at very low concentration level, we cannot detect those organic pollutants. So what we can do, we can improve the sensitivity of this Raman technique by designing the optical platform, like surface enhanced Raman scattering based platform, which can enhance the overall signal molecular vibration corresponding to that particular molecule, and also then it can enable the low level detection. So this is basic fundamental how what is Raman spectroscopy. One is what is Raman scattered signal and how it is different from the Rayleigh signal. So in the Rayleigh signal, you don't have any loss of energy, while in the Raman signal, either you have gain or either you have loss. And generally, we look for the stock shift where you have loss of the energy, the gain of energy, the probability of that signal is very, probability of that phenomena is very low. So the signal sensitivity is also very poor. So we look for the stocks line for any kind of the Raman based detection if you want to do. So the important part in the Raman based detection is the design of a suitable sensor platform, or we can say a suitable surface enhanced Raman scattering substrate. And the important criteria in this substrate design is there are two mechanisms by which we can enhance the signal. One can be electromagnetic enhancement and another can be chemical enhancement. So these two factors can allow the capturing of the light, confinement of the light, as well as the better interaction of the light with your molecule, which is absorbed onto the surface of the substrate. So we have been working upon exploring MXene as a optical platform for the organic pollutants with the target towards POPs. But right now we are trying to develop this platform by using methylene blue as a model organic pollutant over here. So what we have done, we have utilized this MXenes. We have synthesized this MO2C based MXene system. Now, before I go to the findings, the results, you might be wondering why MXene, what is so special about the MXenes? These MXenes they are emerging class of the 2D materials. They have very high electrical conductivity and their surface chemistry is very excellent. So because of that surface chemistry, it can enable the chemical enhancement. And these MXenes, they also have the plasmonics characteristics, which can allow to have the electromagnetic enhancement. So you can have two phenomena in a single material, which can enable the low level detection of the pollutant which you are targeting. So what we have done, we synthesized the MO2C gold MXene based system. We started with the max phase, which is a standard process of synthesizing MXene. So we started with the max phase, and then through etching process and delamination process, we obtained this MO2C single layered MXene. And then we utilize the in situ synthesis process to load the plasmonic structure, nanostructure, which is gold over here, to further enhance the performance of this substrate, that is MXene. And then we fabricated the substrate utilizing this hybrid system for the detection of the MD as a model organic pollutant. So this is, you can see how we have done the optimization in terms of the loading of the gold nanoparticles onto the MXene nanostructures. So we can see there is a plasmon peak corresponding to gold nanoparticle, and we also have a peak corresponding to the MXenes. And from XRD analysis also, we can confirm that whether we could obtain the MXenes or not. So like you can see, the one of the basic criteria which confirms the MXene synthesis is the appearance of peak at around 6 to 8 degree, which is not there for the max phase. So this confirmed that we were successfully able to remove the gallium from the max phase, and we could obtain the etched MXene, which was later delaminated. And while in the hybrid, we see that we have the peaks corresponding to the gold at 38.26 and 28.3 and 64.7, which correspond to the 111, 200, and 220 plane associated with the gold nanoparticles. We also did further morphological analysis in terms of their HR temp characteristics, which also further confirmed that the synthesized MXene are few layered, and there's a loading of the gold nanoparticles. You can see there's a uniform loading of the gold nanoparticles throughout the MXene sheet. And these results are corresponding to the high loading. Like we did the optimization in terms of the loading of the salt concentration. So if we are loading beyond a certain concentration, there is an increase in the particle of the size, and also there is a variation in the shape. So with an optimized condition, we utilize the optimally obtained hybrid, and we started studying it as a substrate. So this is the preliminary screening we did, where you can see if you are using a blank silicon as a substrate, and the silicon loaded with only MXene, and the silicon loaded with the hybrid. So we could see there is an enhancement of the peak corresponding to 16, 20, 20. And also the other vibrations also we could easily make out when we are using the hybrid in comparison to the other normal substrate in the Raman technique. So we did optimization further in terms of the loading, different kind of the loaded hybrid we synthesized, and we could see there is a very good signal enhancement we could observe in all vibrations corresponding to MD, but we do generally a comparison corresponding to 16, 20, 20 centimeter inverse. So you could see that at for a 15 microliter, we have around 20 microliter, we have the highest signal. So we took it as an optimal substrate, and we studied it for different range of concentration of methylene blue. So we could detect even to a very low concentration of 0.5 micromolar. And this we could detect with a 785 Ligand, which otherwise in the literature previously it was reported that MO2C MXene had a very poor signal towards 785. So you can see that when we made a hybrid with the gold, the MO2C could not only respond to 785, but it also enabled a very low level detection. So this is like other kind of similar substrate we designed from, again, a carbon-based nanostructure. I will not more in detail of this. So yeah, fine. So this is all about different kind of materials and the platform which we have developed for the detection of the water pollutants. So this is all about from my side. I'll be happy to take the questions.
Thank you, Dr. Pooja. Thanks a lot. That was a really Nice talk. Your group has been doing a lot of things, I guess, and most of the things relevant to the need of the hour. So it was very nice, and I request audience students to ask their questions. They can either type them on chat window or they can unmute themselves and ask. In any case, meantime, they ask questions. Dr. Pooja, I have a general question, not related to the research work, but there are a number of students who want to choose the same career path as you did. So can you guide them how you ended up being at CSIR? Because a lot of them dream to be scientists there. So what route did you take?
Okay, actually, after my +2, I did my BTech from Kurukshetra University. And during that, I prepared for the GATE exam and I qualified that. And I entered into IIT Roorkee, where I did my master's program in nanotechnology. I was from the actually first batch of the MTech Nanotech program in IIT Roorkee. During my MTech program, I also got this Commonwealth Fellowship, and I visited Canada, where I had, I think, significant exposure in terms of the research, what actually research is all about. And during my master program also, I had an exposure working at NPL. So from CSIO, from IIT Roorkee, the CSR labs came for the campus recruitment. So I got selected through the campus recruitment to CSIR lab. So there were around 4 CSIR labs were there. So one of the lab was CSIO. So I joined CSIO through campus recruitment from IIT Roorkee, but that was more or less kind of ad hoc position, like that for us some period. So for the 2 years, we had to prove ourselves that we are good enough to be taken further. So after 2 years, there were again the open recruitment where we had to compete with all the applicants who applied in an open advertisement. And then I finally got selected in CSIO as a scientist. And along with my responsibility as a scientist, I also did my PhD from CSIR itself, that is from ACSIR, Academy of Scientific and Industrial Research. So maybe I would like to say more or less like the exposure is very much important if you want to work in the field of the research. And especially in the research, your passion is also equally important. See, when I joined, I had only 1 or 2 publications in my profile. And I had to compete with the senior scientists who are well established here, and coming directly after MTech and competing with the other group of people it was tough. Okay. But what I did, I tried to create my own group. I started working with the even short-term training projects, the one who were coming for 6 months or maybe for 4 months or maybe for 1 year. For the internship in CSIO. And it has been track record of my group that every trainee work has resulted into a publication. So as on today, I have around 72 publication in my profile. So this has been possible because of the sheer, to take the passion to prove myself, and openness to learning, improve myself. So those were the certain things which made me here, whatever little I am today. So see, challenges are there in the life of everyone. So you have to continue working, and you have to be open to learning and criticism. Keep doing your work.
That's really inspiring. And I see a raised hand by Anuj. Anuj, you can unmute yourself and probably ask a question. It would be better if you could introduce yourself first. I think we are not able to hear you. Anuj, probably there's some audio issue. If you can type your question in the chat window.
He's muted actually.
I think, yeah, we have to.
Oh, he did unmute himself for a brief period of time, but.
Ananya, can you unmute him?
Okay, ma'am, I'm trying. Ma'am, Anup sir is already unmuted.
I think you can type your chat, type your question in the chat window. There are some issues connecting. So what's next? Like, what do you plan to do next after this in your research work? Like, are there any long-term, short-term goals for you?
Yeah. So like I said, the sensor work, I am more or less focusing towards bringing this product into the market. So one of the important requirements for taking any product to the market is the generation of a lot of field data of the device. So that is my, in one of my collaboration I'm doing with the this pollution control board people, where we are visiting different places into the Punjab, like different villages, and we are generating the field data so that we can transfer the technology to the industry. So in the second aspect, which is like catalysis, which is now my major focus. So I am trying to develop the large scale electrode for the green hydrogen generation. And also I am trying to develop, like take my materials, whatever these 2D materials I'm developing, I'm trying to investigate them, study them, and also scale them as a filters, which can be used for the indoor air purification. So overall aim is whatever research we are doing from material science of point of view, we are more or less focused towards their translation. So that is my current focus of the book.
Okay, that's great. Yeah, I think Anuj said he's going to rejoin. Probably we can have a quick group photograph, because you said you have prior commitments after the talk. If everyone can switch on their videos, I can take a quick group photograph for our records. I request everyone to kindly switch on their videos. Few more people, so that at least we have photographs in the first frame. So if more people can please switch on their videos. So 1, 2, and 1, 2, and okay. I'll probably take another one. One, two, and great. So thanks, Dr. Pooja. We'll wait for Anush if he has.
Yeah, he is there.
Am I audible?
Yes, Anush. Yes.
Yeah. Thank you so much for accommodating me. Actually, it's a wonderful talk, and actually, I have a small 2 to 3 questions that, as you have explained about that, you are using. I think you are just going for the detection only, or is there any remedial measures that you are taking while after going for that pollutant detection and all?
No, all these whatever I discuss is more or less for the detection. But like I told about the catalysis part I'm exploring for the wastewater only. So there I'm trying to generate energy as well as undertake the treatment. So why I'm taking this problem? Because generally when I approach these stakeholders, the first question they always ask, you have detected, now what next?
Yeah.
So that's what I think a question always asked to us. So I now thought, let me combine my expertise in the domain of water and explore and do the treatment as well as generate energy out of it.
So is there any difference or altercation when you are detecting? Is it quantity based? Because there might be a chance that some area or some location has low level of pollutant and some have very high concentration of pollutant. So how you are going to differentiate that it's a low level or high level concentration? Is it based on this any sensitivity or sensor, or how you are detecting that? Is it where there is a low or high concentration?
See, there are set permissible limits for every kind of pollutant, which is defined by WHO and BIS in our country, like BIS. So we say if it is below this, then it's low, it's safe to use. If it is above that, we always say it's unsafe. If it is way higher than the range which is limited, it's basically marked as red, that not fit for use. So in kind of the kit which we have developed, which is there even, I think in all the FTKs, there are range defined, so that tells your level is in this range or in another range or that range. So the FTKs mainly does the primary screening. So they are kind of a semi-qualitative analysis of the water. So that saves a lot of sampling in the beginning, because you need not to collect the sample everywhere, every time. And you can engage people more over there into the, water is an important subject to be discussed. So you can engage people. So what we are trying to do is we are trying to develop these FTKs for the pollutants, which for those the FTKs were not existing, which are not indigenized. And also there were no kind of IoT solution were available to quantify the response, so that we can engage the people more. That's all the purpose of all this work we have done.
Okay, it means that this kit is efficient to detect any different levels of that pollutants.
Yes.
Okay, and then final question, that when I think you were just talking about that most probably any chip based or the lab setup only, or is it a closed system based approach or the open system that we are just going for that field and ground level trials or something like that to get rid of?
That's what I'm saying, that we are in now this year we are more into the field. So we have already done one visit in the Punjab, and we are doing this work with the PWSS. So where they have given us some villages where they reported that there is a level of selenium which they could detect by their ICP-MS system. So we are testing our kit in those villages, and we are generating the field data.
Okay, thank you so much. Thank you so much for that informative talk.
Thank you. And yeah, again, I definitely, like I said, I worked with the intern. I grew because of intern. Now I have 6 PhD students with me full time, but I definitely look for the good students, good PhD students who are willing to work at least maybe for 4 to 6 months in my group. So there are a good set of problems which I can offer. So those who are willing to work in the domain of material science, they can write to me, they can reach me.
Okay, great. Is there an official portal where they need to apply, or they can directly approach you? Like, I don't know how.
See, we have the open advertisement twice in a year. So for the winter, there will be a call, but otherwise also one can approach me with their CV. If the CV is good enough, then we can get the approval directly from our director also.
That's good. That's a really catch point for students. I hope the interested one are listening, but I will definitely float this message, and I hope it's of use to many. And thanks a lot, Dr. Pooja. I would officially like to thank INYAS, your efforts, and Ananya has been with us for all these lecture series. Thank you so much for handling the Zoom so well. Thanks to Yatin Batra, who took the initiative of these Teach for Science lecture series. Yatin, if you want to add something to it.
Yeah, I was going to say that I may not be able to find speakers without help of Dr. Pooja. Yeah. So thank you, ma'am.
I'm thankful to my INYAS friends who could agree on my just one message to speak on this series. So I think it has gone very well, and every week we could have very good speaker.
Yeah. So yeah, Anuj, maybe Ananya ma'am will be sharing the YouTube links we are uploading. They are uploading these lectures on INYAS YouTube channel, and we will share you on your email if you have registered through the Google form. So over to you, Dr. Bindia.
Yeah,
I think there was one question which came to me. Maybe let me address that. The question is from Diksha. She's asking how I am detecting the organic pollutant with the silicon this hybrid. Okay. So Diksha, basically what I showed the hybrid, that is not for the removal. Again, whatever platform I have discussed is mainly for the detection. So the previous color-based platform or fluorescence platform, they were for the detection of the inorganic pollutant, mainly the heavy metals and metalloids. And the stars-based platform, which I discussed, they were for the detection of the organic pollutants. And I showed the results using methylene blue as a target, like model pollutant. But what we are going to do, we are going to extend this platform for the POPs, that is persistent organic pollutants. I hope I'm clear to you.
Thank you, Dr. Pooja. If there are no further questions, I'll take permission to officially end this lecture series, Dr. Pooja.
Yeah, sure. And I look forward to future collaboration with Priyas. And I think any regional language series, if Priyas would like to take, that would be something of interest to INYAS Chandigarh chapter as well. Maybe some even the field visiting to the schools in this Punjab area. So maybe definitely we'll discuss.
Thank you so much. It was nice collaborating with INYAS. Thanks a lot.
Yeah, thank you. Thank you very much, Ananya, for coordinating the series from INYAS side.
Welcome, ma'am. Most welcome. Shall I end the meeting for all, ma'am?
Yes,
Yes.
Ananya, you can do so. Thank you everyone for joining. Thank you.